This is a painful fact that all AI models will stop learning as soon as you deploy them. But NVIDIA is truly changing the game. Because the new proposed AI architecture can let AI models continuously learn as long as you're using them. So it reads your prompts and updates itself. It manages both long-term, short-term memory all by itself together. So as long as you're using it, it is keep learning. And it can be up to even 3 times faster compared to larger prompts that you have with different AI models architecture. In this video, I'm going to show you what is their secret sauce and how you can use it right now in your own projects. Let's check it out. This research is the result of collaboration between NVIDIA and some other institutes and universities, namely Stanford, which they are proposing an approach that how we can let AI models learn as we use them, which they call it end-to-end test time training. So you know that when we deploy AI models, specifically AI agents in place, although we can use some memory or RAG stuff to keep update them, introduce them some past behaviors so they'll adapt themselves, but it's not really training, or better to say they're not updating the model by itself, like parameters and stuff, to let them continuously learn. But this approach that they're proposing is truly shifting how we are looking at context or prompts, so we can use these context or prompts as training data set to continuously train our model. But how? They are mentioning that we keep seeing LLMs with larger context window in the news, along with promises that they can hold entire conversation. So we are checking out which model has the larger context, 1 million, 2 billion, 10 million, and we're hoping that it truly learns everything as we push to the prompt. But that's not truly the game, and also maybe it's the wrong way to think about shall we really push our efforts to create models with larger limit, or we can maybe make these models infinite in the context by a trick. But what is that trick, or better to say a shifted vision? In order to answer that, we need to go back and maybe check how truly human brain learn and compare that with LLM memory, which they have differences right now. So they're saying that humans are remarkably good at improving with more context in the form of life experience. So that means when we are in a lecture and we are listening to the teacher or professor, although we are learning as we're experiencing that teaching class, but at the same time, if you ask me what was the exact sentences that my teacher told me 5 years ago or 10 years ago when I was passing some lectures in, let's say, AI or machine learning, I have no clue. But I still remember the whole context or the main key components of that lecture, so I can now understand ML articles or read more about it or update myself. So that means human brain doesn't necessarily keep memorizing all specific tokens of past experience. We compress by our nature of design how we are learning through interacting with our past experience, and then we decompress those key components, not all the details, to continuously learn. And the whole point of that is this is not the case with LLMs and LLM memory, specifically if using full attention layers with KV caching and stuff, which we're going to talk about that shortly in more details. We are truly paying attention to all details of previous tokens to generate the next token, which shouldn't be really the case. And let's see how we can try to convert that towards something like similar to human brain. This slide sort of compares human brain versus LLM, or better to say how LLM currently works and the proposed approach, which is like human brain. So on the left side, this is sort of the current paradigm when we talk about most of language models or foundation models. We have sort of a model that we can keep pre-train them, but as soon as they are trained and deployed, we cannot truly let them continuously learn. Yes, we can do some fine-tuning or potentially apply some post-training, but it's not the case that as soon as you send the prompt, at the same time that it's responding to you, it first tries to learn and train itself and then respond to you. So next time you ask similar questions, it behaves with adapting itself and learning from the past experience. That's truly not the case with the current paradigm and architectures we have. So what happens, as soon as you send the prompt to these transformer-based models, it tries to convert those words to tokens and embeddings and then generate something called KV cache. Technically, there are large matrices that each token and its embeddings is represented as a key value matrix. And as soon as it starts to generate the response for you, it has to know not only the KV value of the last token in that sentence, which was your input, and also all the previous words of that sentence or context you have in the prompt. So think about it. When you have large prompts, it's trying to accumulate itself with more tokens, more KV cache, and keep keep all of that getting saved in memory. So not only it's gonna be a little bit slower, but also potentially be more costly because you are dealing with a lot of KV cache values that you keep gaining them. Because with the attention mechanism in these transfer models, they need to really understand all these past tokens and sentences to pay attention to all of them to give you or predict the next token, which is the output that they are generating. But to shift the paradigm towards a continuous learning and how human brain learn to compress past experience, as I just mentioned, and really remember the key components, maybe with now this new paradigm, we're going to have a live model that updates itself, potentially even parameters, or better to say weights, as you are using it. So this is truly continuous learning. Different methods like RAG stuff that you retrieve some knowledge or you retrieve the memory out of past experience, they're sort of mimicking that they are keep continuously improving the model, but none of them are continuous training. And this is sort of the first time that we are going to talk about different approaches and what NVIDIA is proposing. But there's a trade-off here. You might say that this is good, that some attention mechanism that can truly memorize all the details of the past components or past tokens, although we talked about it's costly, it can be potentially expensive, but you have perfect recall. But it comes with potentially performance or speed trade-off. If we compare, for example, transformers with full attention, as long as you're increasing the length of your prompts or context here, it's not necessarily going to have bigger loss, or it doesn't deteriorate the performance because it can potentially understand all the details. It's not really the case that always the loss is going to be the same. Obviously, larger prompts are more or less immune to some faults, some hallucinations, or forgetting some facts, but they're proven to be better on previously remembering what has been going on within that context compared to some other architectures like RNN, Mamba, or DeltaNet, because they might be faster and they might be also cheaper, but at the same time, when we increase the context length, they become bad on the performance, so the loss get increased. So I'm stuck here if I'm gonna go with something speedy, cheaper, but losing performance versus vice versa. But NVIDIA's new approach, which is TTT-E2E or test time training with end-to-end process, will come up with a trade-off that get both of them, which is good in speed and also recall good, and at the same time it can be cost efficient. Let's see how. In their proposed approach, which is test time training is not new. It has been there, but they are having another additional layer that they call it outer loop on the top of test time training. I wish I'm gonna tell you what that is. But let's just start with the inner loop. So there are two phases, inner loop and outer loop. In inner loop, as you can see, let's say right now in my current state that I am, if you follow my pointer, right now we have trained a model that you're using with Gemini, GPT model, or any open source model. They have the weights that they have been pre-trained, so you can start asking your question. But as soon as it starts to actually predict the next token to respond back to you, at the same time it is updating itself. When we talk about updating, we are truly talking about calculating the gradients, going back and updating the weights. This is typical multi-layer perceptron architecture that you go back and update the weights of the different layers. So they have an MLP component that goes back and update, and I'm going to talk about which MLP components, not all of them, not all the weights. And then it does evaluation, and based on evaluation, go back and update the model. So next time you try to ask another question from the model, it is now a new model because it's sort of continuously learned. Not new model, it's the same model, but has learned something based on your past prompt. And it is continuously doing that as long as you're interacting with it live. What they're proposing has a secondary layer. They call it outer loop or meta learning. So why they're proposing that? There is a caveat with this TTT approach, which is the inner loop we just discussed. Because when we do this continuous updating some parameters or weights as we interact with the model, there's a greater chance that we lose the whole bigger picture, that the model need to learn so many things and just update itself tiny as you're interacting with the model. And we gotta make sure that when the models keep learning, it is learning in a correct way. So how do we make sure that model is also learning how to learn? That's why we need to zoom out and update the initial weights of the model based on how this inner loop is working. So to keep it simple, when we have different weights getting updated through batch of, let's say, prompts, batch of context coming in live to the model, we zoom out, go back, what was the initial W that finally this inner loop got updated, then we shift it to the outer loop, we go back to initialize that weights again based on this inner loop workload to see if the inner loop interaction and updates of weights is truly helping the whole model to get better. So that's how this inner loop and outer loop dependency is helping the model not only continuously learn, but also learn how to learn without catastrophic forgetting of all the stuff that it has learned, or through making more hallucinations or suddenly breaking the model. That's going to help us to have a control mechanism of keep learning as we're using the model. So with this approach, this is how they do in inferencing. Instead of using full attention, they are using sliding video attention, or SWA. So what does that mean? They're saying that up to, let's say, maximum 8,000 tokens, I want to pay attention to the past tokens. I'm not going to pay attention to the whole tokens generated like full attention, which comes with its own caveat. So I keep it 8, but you might say, but if my prompts are much more larger, the context is huge, that means it's going to ignore everything before that 8K token, because there's no key value generated for that. That's why they are adding this mini batch, which they will take it from your prompt to go and update the model. And because model is compressing your prompts and context as it is learning them, so there's a great chance that it can recall the main components back. So we don't need to keep looking through all the tokens previously generated beyond that 8K, because those contexts are really updating the model by itself. And when we talk about updates or weights updates, we are truly compressing the knowledge through those weight representation of the model. This is what we have the mini batch. And what they mentioned, that a rule of thumb, that window size for sliding video attention is typically larger than the batch size, just FYI. And this sort of hybrid system is now introducing a hybrid memory system. By hybrid memory, I mean both short-term and long-term. What is short-term memory here? Short-term is exactly what we're talking about the model right now, which is the attention part, that 8K, which is already proposed and we have it in the context. But that long-term memory is those mini batches that you're using them to update the weights of the model that can be decompressed and being learned and be used for generating the next response for you. So that's what I talk about, that long-term and short-term memory couldn't be just rack, or couldn't be just fixed or dynamic prompts. It could be the model by itself that can help us to not only continuously learn, but also we are sort of proposing a memory system here as well. That's how we are reimagining what we think about memory or long-term memory through the dynamism of a continuous learning picture. When we talk about updating within that inner loop or updating weights, multi-layer perceptron, are we truly changing all the parameters or weights of the model? Absolutely not. What they propose in the paper, they are not touching any attention layers or norms. They do actually propose a secondary block of multi-layer perceptron. They call it static and dynamic. The reason they're proposing this block or multi-layer perceptron, which is a neural network, they want to make sure they preserve the pre-training knowledge. If you, let's say, take, I don't know, Llama model, open source model, or something that has been already pre-trained, we are not going to suddenly change it, because that's going to be costly and also get some catastrophic results. So that's why we are going to propose this dynamic MLP beside the static one, and they're going to update this one based on the context that we keep using with the prompts. And this one is only 1/4 of the blocks. So we're going to balance the compute with capacity, and this is what they are proposing. So they wanted to check and see, okay, now we are getting back to that trade-off conversation we had, which was the speed versus the latency versus the performance of the model. And they realized that, wait a second, when we tested our TTT-E2E approach, which is what they propose, compared to, let's say, full attention transformer, which can recall everything perfectly because it has KV cache of all the tokens, they realized that, well, we have same loss as long as we're increasing the context length. So they realized that at context of 128K, that means when we have the largest amount of prompt within their test spectrum, they realized that they have sort of the same performance compared to transformer, which was sort of the baseline, full attention, which was the baseline that they were comparing with, which is great news. That means with this approach, we are not talking about losing performance or something. So we are not sacrificing the performance here. Okay, that was about performance, but what about speed? Speed was very interesting. They realized that at 128K context window with using H100 GPUs, their approach got 3 times almost faster. And the reason is when we use full attention with transformers, we have to really again store all those KV values and the dot products between them and utilizing them for generating the next token. Not only consume a lot of memory and compute, but at the same time that can take some time. That's why, because they're using a sliding window and using those mini batches to compress the knowledge back to the model and they can decompress it later, they realize that when you really have large context, it worth to give it a shot because maybe you can have 3 times faster AI architecture. But there's only one caveat, or instead of using the word caveat, better to say what going to be the use cases that TTT approach is good one or it's not a good one. Well, if you check out this chart, this is just a conceptual demonstration, not the precise numbers here. But if you check out, when we have these full attention transformers, they are good for perfect retrieval. That means you can technically have exact details in the prompt. Let's say you have a model like Gemini that has 1 million token limit. It is good to retrieve all the exact details within that 1 million context. But if you go with TT approach, they are not in a retrieval mode. They compress those prompts or context all the way back to the model by itself to be decompressed later. So it is like human memory. It's not going to really remember every single words that my teacher lecturer told me 10 years ago in a course, as I told you the first example, but I know some context and have learned the key components so I can use it for learning some new stuff or responding back to you if you ask me some AI questions. So this is truly the idea of TTT compared to like full attention. So use the approach for when you have large documents, large context, that you're not looking for exact retrieval, you just want to learn something like a large code base or books, this is good. But if you want to use something for exact extraction or some database lookups that you want to retrieve something, use full attention. So RAG gotta be still there when you want to retrieve a fact or something, that's still a feasible approach. But think about if you want to continuously learn like human brain for some facts that can be used, let's say for personalization of AI agents or adapting itself as it interacts with the user, their approach gonna be a good shot. The other constraint is that when you want to do actual training, training a model, I mean pre-training and also having this continuous training, you might see some 3.5 times slower than startup transformers. We are not talking about actually the time that you inference the model, not necessary, within again the training. And potentially the mitigation roadmap would be having some custom kernels that they're going to optimize the attention layer to let this TTT approach becoming a little bit faster. And the reason that is slow because it calculates gradients 2 times. You have that inner loop and outer loop. And outer loop is getting updated based on the gradients of the gradients. So that's why that sort of new mechanism of outer loop end-to-end potentially might cause some latency. But again, as they mentioned, when you have large prompts, that attention layer becomes slower because of huge KV cache. That's the time when TTT approach shine to becomes even faster. So to summarize really the whole point, the solution to the long context problem isn't just a larger context window. It's a model that learns from its context. This is really the whole approach you're thinking about, to have it good recall, good efficiency, and at the same time, without really handling the context window in truly just RAG or different ways, and use the context to actually continuously learn. Now you might ask me that, okay, how can I use this approach with any other models? Can I use it? The answer is yes, or partially yes. If you want to, as of now, use this approach with any open source models, you can, but within the context of that inner loop. So let me go back to that slide to explain that better there. If you take any open source models, namely Qwen Llama, you can technically have TTT applied in a way that just updating some finalized layers of MLP through the prompts that you're using them through the inner loop that we discussed. But if you want to go to the outer loop and have that end-to-end process applied on TTT, you have to go back maybe to the initial model architecture and propose that new sort of dynamic versus static MLP and really change a little bit of the architecture and do heavy pre-training or maybe heavy fine-tuning to truly let the model initially be ready for continuous learning. Because all the model architecture that has been trained so far as an open source, they are not trained with the context of this model is going to continuously learn in the future. That's why to have a model truly apply this approach, you have to go back in the pre-training stage or heavy fine-tuning to truly change the behavior of the model in a way that can truly be ready to continuously learn through the inner loop and outer loop. But still you can semi-apply to just change the final layer parameters as you have the prompts in place. And good news, they have already open sourced the code, so you can check this out and help get it as a help for applying their approach if you want to fully or semi apply your solution. This is the GitHub repo they released. This is based on the paper that they published, and also to make sure that their solution is end-to-end reproducible, they have released this open source code and it's implemented in JAX. So I will add the link of this GitHub repo and the paper as well. The full paper has much more details about their benchmark and the results they got, so I will have it as a reference for you. It's gonna be in the Discord channel. The link of the channel is in video description below. When you go there, there's a link that has all the references of all the videos I have published so far, so you can take a look and let me know if you like the video. I would appreciate if you can like icon. Make sure you share your thoughts and comments in the comment section below and subscribe so you won't miss the next video. Thank you so much.